Hey everybody. So what this video entails are problems that I find fit the themes of expected questions that will be on test 4. Now, when I say the themes, what this most closely resembles, not exactly, but most closely resembles, are various question types that may be asked. And the problems that resemble these question types the most are, I would say, are closely resembled in the study guide. Now, there are a lot of variations to some of the problems that I discuss in the study guide, which means that in no way is this an implication towards simply looking at just the study guide and just the practice test and have that be your main source of studying. In my opinion, the best way to study, this is my suggestion, is to see the type of questions that what my study guides say. For example, one of the problems is write a bunch of logarithms as a single log. I have one example in my study guide, but you should look at that problem as I should look at other problems that also ask that same question type, either in the notes, maybe in the practice test, and maybe on the homeworks, and see if you could get yourself a good idea of how those problems are oriented. That would be the best way to study for this test. It's not to just memorize one type of problem, but seeing what the question is asking for a question on my study guide and going back and reviewing various questions that ask the same thing. That is the main theme or the main focus I want you all to have when you go through this video. So the best way to prepare for this exam is by determining what the questions are asking on the study guide and going through all the available resources. You can even schedule a one-on-one Google Meet session with me, but other than that, I'll go ahead and start with the first problem for the study guide. So for example 1 here, we're going to consider this exponential function. So just a number base and a variable exponent, and just gonna plug in some numbers and see what comes about from those. And so part A here just wants us to start off by plugging in -1 into the function and seeing what the output yields. So just simply plugging in -1 for x. So that's 2 now raised to the -1 plus 9. And so remember what -1 does as an exponent. It means the base becomes flipped. So the negative exponent means that 2 will now become 1/2. You can also do all of this in your calculator, that's perfectly fine. Just make sure you know how to put this in your calculator. 2 raised to the -1 power. But in any case, you'll get 1/2 plus 9. You may even get a decimal version of this. You might get, say, 9.5, but just keep in mind that there's those nitpick situations where I'm pretty sure for this problem it says type in an exact fraction. So you need to know how to convert this as a fraction. And this is, in fact, pretty sure it's 19/2. Let me make sure. Yeah, it's 19/2. So it will say after this, type as a fraction or something. So that would be the first part, 19/2. And then immediately after that, it wants to know the ordered pair. So the ordered pair, and you should all be familiar with this idea now. It's just, well, the notation always starts off the same. It's some parentheses, and it's the x value and the y value. The x value is -1, y value is 19/2. So not too bad so far. But again, keep in mind what the negative exponent does. For part B, it says, well, let's consider when the y value, or the output, is 17. What happens to x now? So that means we're setting the whole function equal to 17. So the whole function up here is now equal to 17. We solve for x now. And we do, this is just true in general. If we're solving in an exponential function type problem for x, we need to get the exponential function by itself. The exponential function is 2 raised to the x, and plus 9 has to go. And where does it go? To the other side. So we subtract 9 on both sides, and what we get there, it seems to be 8, is equal to 2 raised to the x. And from here, you can either use a natural log, or even better, you can get a common base, like we did when we started off exponential functions. Because 8 can be rewritten as a base of 2. In fact, 8 is simply just 2 raised to the 3rd power. So we changed 8 to 2 cubed, and the only reason we did that is because the common bases cancel. 3 is equal to x. And so that tells us what the x value is. And from here, part B also wants us to determine the ordered pair. So just like in part A. And so don't get confused. Don't put 17 comma 3. And in fact, I think the problem is kind of tricking you by making you think it would be that orientation. It would be 3 comma 17 because it's always the x value and then the y value. But other than that, that would be example 1. So for example 2, we're simply solving the equation here, which means we will conclude with x is equal to something. Now in this problem, as we had before in a previous section, so you have to think to yourself, what happens when there's 2 logarithms? What do you have to do? And in this problem, I think the best motivation here is to get the logarithms together. Because once you're adding or subtracting logarithms together, we have rules for that. So we're going to subtract the logarithm on both sides. I'm going to bring this one over. It really doesn't matter, but I am going to bring this one over. And what we will have is exactly this expression here. So all I did was bring this over. Because once we have 2 logarithms subtracting one another, then we can utilize the quotient rule in this case. So the quotient rule, if you don't remember it, you do need to know it for the test. It simply allows you to combine logarithms, the difference of logarithms in particular, as one logarithm with the same base, which is understood to be 10, where this part goes in the numerator and the negative part goes in the denominator. And when I say negative, I mean what's on the right-hand side of the difference. And all of that is still equal to 1. So all we did was take 2 logarithms, use the quotient rule, because this is a difference, combine them as 1. Because once we have a single logarithm, now we can use that loop method that I was talking about. And I did mention the base is understood to be 10. So what we have now, in fact, I'll do this in a different color just to emphasize it. So now we have 10 raised to the 1st power is equal to, well, the fraction here. And we do have 10 raised to the 1st power. I'm just going to simplify that as 10. So I think I saw a few problems. In fact, I do have it written here as rewrite the given equation without logarithms. There are a few problems in the practice test I noticed that ask this, and this is one of them. This would answer the first part right here. Because there technically is 2 parts to this problem, the way it's asking for it. So rewrite all of this without logarithms. There's the log notation, no more log notation. And now for the second part, here now it says to solve. So we'll go ahead and solve for x from here. So the first thing you should think is, well, is a denominator, which means you can clear it using the least common denominator, or cross multiplication. So we will use cross multiplication. Over on the left side, of course, the denominator cancels out with that LCD. That is now 5x plus 1 is equal to 10 times x minus 5. I am going to go ahead and distribute as well. So here I'm distributing to get here. And I'll just go ahead and solve for x. So this is combining like terms. And then finally, we get that x is 51 divided by 5. And that would conclude example 2 here. We move on to example 3, which is a problem that we saw in the exponential and logarithmic equations section. And this is one of those substitution-based problems. And as I mentioned in the introduction of this video, this would be one of those problems that I would suggest you look at other variations of. We went through quite a few variations in the notes, so please refer to those problems. In fact, if you do the practice test, if you attempt the practice test 2 or 3 times, I'm pretty sure you'll see variations of this, so just make sure you're comfortable with various types of ways that they can throw the substitution-based problem your way. But all of that aside, let's go ahead and try to figure out what the trick is here, because I did say it's a substitution problem. That should be very apparent by just this 3-term form that is going on here. However, substitution cannot be applied quite yet because this x plus 1 in this middle term is ruining our declaration for what the u sub may be. So what we need to do, this 3 to the x plus 1 here, let me try a different marker here. So this would be, so this is kind of work off to the side. What we're doing is manipulating this problem using one of our exponential rules. If you have an addition in the exponent, you can break it up as a product of exponentials. And so that would be 3 times 3 to the x. And that is exactly what we're going to utilize here. So again, that's exactly what we utilize here. So we're rewriting this term to become this term here. And now we can go ahead and make the appropriate substitution. In particular, u is equal to 3 to the x. This will be our substitution, and it works out perfectly because there's no plus 1 in the exponent to throw things off. Now it's just 3 to the x, and that's exactly what we declare. So by virtue of this declaration, this term here becomes u squared plus 3u minus 54 is equal to 0. And from here, we treat it as if it were just a standard quadratic equation. So here it seems like it would factor as plus 9 and minus 6, which makes sense because their sum would give us 3, their product is negative 54. So we get 2 u values, negative 9 and positive 6. But remember, anytime we use a u substitution, that is not good enough. The u values are not good enough. We do need to plug them back into our substitution. And I'll go ahead and write it down again, just to remind everyone. And so here, we want to explore both situations, or both values of u. One of them is negative 9 for u, and the other one we found was 6 for u. Now, I mentioned this before when I went through these types of problems. One of these we can get rid of immediately. Back to this one. An exponential function, just like a square root function, cannot output a negative. If you're not able to see that, then the immediate next step you would do here is apply the natural log on both sides. And I'll kind of explain that process for this one over here. But if you make that observation, you can cancel this out immediately. Over here, as I mentioned, you would apply the natural log on both sides. And this is a common thing to do if you have an exponential function that is isolated and the variable is stuck in the exponent. That's when you apply the natural log to everything as your first step. Over for this problem, if you would have applied the natural log to the -9, that would give you a domain error. So that's something to keep in mind if you can't remember this rule. From here, the reason we did this is so we can bring the exponent to the front of the corresponding logarithm. That's the main reason why we do this. And now we just fished the exponent, or the variable, out of the exponent. And from here, since this is a product, we can divide both sides by this natural log of 3 quantity and conclude that x is natural log of 6 divided by natural log of 3. And that would be your answer for example 3. So for example 4, you might recognize this one as the last question from the section on exponential growth and decay. And when I talked about that problem, I initially said, I don't expect this problem to be on the test and just follow what I say. Well, this problem will be on the test. Some variation of this problem will be on the test. This is the only one I will tell you about, because I figured I'd rather just let you all know about a problem I initially said you shouldn't expect. Anyways, this problem, make sure you're familiar with this problem and the problem that I talked about in the notes, in particular parts C and D, not so much A and B from that problem, but parts C and D. And the parts I'm going to do here will also resemble parts C and D. So it says something about, I think it was some American bald eagles. It gives you this somewhat familiar function or equation. And part A says after 3 years, what's the output ultimately? You plug in 3 for the obvious t value, t for time, and figure out what everything equals. So if anything, part A, it's manageable, but it's just fairly tedious. So let's just go ahead and see how that works out. So all we're doing, so that is an 83.33, e raised to the negative 0.612, all of that times 3. And as I mentioned, this is part A, it's manageable, just tedious. This is all calculator work. There's nothing to solve for in this part. The only thing to make sure of, if you're going to put all of this in your calculator all at once, I would recommend putting parentheses around the denominator and also around this exponent here, or else your calculator cannot keep track of it doesn't have spatial awareness about where everything's at. So 500 divided by open parenthesis, 1 plus 83.33, and then e, it opens up a parenthesis for you, so that's convenient. Negative 0.612 times 3, close parenthesis, close parenthesis. And I get 34.996. We are going to round to the nearest whole number, so I'm going to round this up to 35. So make sure, if anything, you are okay with that first part, which should be manageable. It's part B that really starts to become complex. And part B, just like how we noticed in the first example we looked at, where the first part asked you to plug in x and determine the output, now they're giving us the output and want us to determine x. So for part B here, what they're ultimately saying is set the whole equation equal to the 300 equals, as they're calling it, and determine the amount of time that takes. this is something you will need to be familiar with for the test. This is the one problem I'm telling you, so you do need to be familiar with the process I'm about to highlight here. Now, if anything, the first thing you do is clear the denominator. The denominator, I think it's pretty explicit here, so let's go ahead and clear the denominator by multiplying both sides by it. From here, what we can go ahead and do is distribute this is slightly different than how I explained it in the other video. In the previous video, I said divide both sides by 300. I'm gonna go ahead and distribute the 300 here though. No real difference between the two methods. I'm going to distribute, and what I get is 300, because 300 times 1 is 300, plus 300 times 83.33. So 300 times the 83.33, and it looks like we get 24999, and then the E stuff carries over. So now we get here. And from here, we need to get the exponential part by itself, so we subtract 300 on both sides. We'll go ahead and move that all the way up here. So upon making that subtraction, so it's simply just 500 minus 300, that's 200. And now we can go ahead and, so if you find yourself in a situation like this, you have to, before you can get rid of the E, before you solve for an exponential function, you must get the exponential part by itself, which means this number in front needs to be divided on the other side. So the E part does need to be isolated. So what we're doing here, and just to emphasize that, we're simply dividing both sides by 24,990. And this will make more sense when we go into the following step. So 200 divided by 24,999. Let's see if that comes out to be a nice number. 24,999. So I get 0.0080, so it does not come out to be a nice number. So we will be stuck having to write this form. Because if you round too early, it will affect your final answer. In MyMathLab, remember MyMathLab's picky. So you have to keep exact answers as long as you can until the very end. Since this does not give us an exact answer, then we have to keep this ugly form. And also though, but I did mention we had to get the exponential by itself, which meant everything that did not belong to the exponential had to be shoved over. But now once we get the E part, we can apply the natural log. And that's still a philosophy we follow whenever we have a variable in the exponent. So the first step there is simply applying the notation. So on the left side, all I did was just tack on an ln. Right side, same thing. The convenient part here is that the ln and the e happen to cancel. So instead of having to worry about bringing the exponent to the front, it just so happens the ln and the e cancel, and we get exactly negative 0.612t is equal to the natural log of 200 divided by 24,999. And all we have to do is one more step, just one more step, to get t by itself, and that's divide by this negative 0.612. So now we get down here, and it's just a matter of seeing what the calculator gives us, because what this problem wants is an exact answer, well, not an exact, sorry, an approximation rounded to the nearest whole number. So this is natural log of 200 divided by 24,999, close parentheses. That negative 0.612 is not in this natural log because we divided it after the natural log was closed off. So we divide that by negative 0.612. And I get 7.889, something like that, but I want to round it to the nearest whole number. So that's going to be 8. So the analog of this problem, or the conclusion, it would take 8 years for there to be 300 eagles. And again, this is a problem you do need to know for the test. So please be comfortable with this process for solving this, but that would ultimately conclude example 4 here. For example 5, we have a $90,000 house, something about appreciation over 5 years at 8%. And this is pretty much asking for 2 different things. One part's asking for you to figure out the amount in 5 years if it's compounded annually versus compounding continuously. So this means we're going to utilize 2 different formulas. So the compound annually formula, just as a reminder, this is the P 1 plus R over N raised to the NT formula. And here, all of the given values, the present value is, well, the current value for the house. 1 plus the rate here, the rate 8%, but we need to convert that as a decimal, so that's 0.08. That divided by n. Remember, n is the number of compounding cycles in a year. Annually will tell us that, so how many times does something annually happen in a year? It's just once. Close that off, all of that raised to the n again, times, and what I'm going to do, I'm going to write t for now. I know t is 5. I did see a problem or two that talked about writing, I think they called it an exponential equation. The first part was write the exponential equation and then plug in for t. This would be the exponential equation part. I don't have that in the notes, but I just saw that. So if they mention anything about exponential equations, it's basically wanting you to plug in everything but time. So that is something I just noticed. And from here, we can go ahead and plug in 5 for t. And from there, that's just a calculator problem. Now let's go ahead and put all of that in and see what comes out. Again, if you put all the parentheses like I have here, it should work out just fine. 1 plus 0.08 divided by 1, close parentheses, raised to the 1 times 5. And so I get 132,000, some other stuff. Yeah, that seems right. And since this is money, we're gonna go ahead and round to the nearest cent. So it looks like that will be 13239.53. And the other part of this is asking for us to compound continuously. So again, I'm gonna build that exponential equation thing that I mentioned. So remember, the initial formula for compound continuously is the PERT formula. As I mentioned, I'm going to write down the exponential equation first, which is a function in terms of t. That's a fancy way of saying we're going to plug in everything but t. So the initial value is still 90,000. E is just e. That raised to the 0.08. And again, I'm leaving the t. So if it does ask for an exponential equation, this would be it. It's just you plug in everything but for t. And then now we can go ahead and plug in for t. In fact, I'll do that on a separate line. Oops, forgot e. So again, it's 5, and again, we plug everything into the calculator. And you should get a number that's fairly close. I get 134,264.22. Again, this is money, so we'll round to the nearest cent. And that would conclude the compound continuously part, and thus conclude example number 5. So for example 6, the directions simply say to solve for x. And I can't recall if it's this one. I've seen a few variations of this one where they want you to first put this as they want you to rewrite it as a statement without logarithms, similar to what we did in one of the first few problems we looked at. But it's already in a very convenient form for us. We can already use that loop method. So if it does ask for rewrite this as a statement without logarithms, then we know exactly how to implement that. Here, the logarithm is already isolated. There's not 2 logarithms. There's not a number in the front that we have to move as an exponent, which means we can jump straight into this loop method. And that tells us 5 raised to the 4 minus x is equal to 1 over 125. And so now that we get here, now we need to consider, okay, so how do we solve this? And it turns out that we can get a common base between these two. Now you could use natural logs, but 125, so let's just think about 125 as a number. What power of 5 gives you 125? Not 1 over 25, 1 over 125, just 1 over, or just 125. So that's to the 3rd power. So 5 to the 3rd power is 125, but since it's 1 over that, then we're not going to look at 5 to the 3rd power, we're going to look at 5 to the negative 3rd power. And even if you want to, what I like to do, I just like to check that in my calculator. So if I look at 5 raised to the, and then I use parentheses, open parenthesis, negative 3, close parenthesis, I get 0.008. If I convert that to a fraction, I get 1 over 125. So it's the 3rd power of 5 that gives you the 125, and it's the negative that brings the power to the denominator. And again, that's all a bunch of various ways of saying that 1 over 125 is 5 to the negative 3rd power. Negative brings it back to the numerator, and the 3 brings it to 125. And again, you can confirm that by using your calculator. And this is something you will need to know for the test. Something like this will probably come up. So this is why looking at a few variations of this in the notes, for example, may be helpful. But once we do this, it's very convenient because the like bases cancel. And you get simply this. And so this says that x is 7. If you did want to see the natural log way of doing this, you can stick around for this part of the video. Otherwise, you can just go ahead and skip to the next one. So if we were to take this problem and look at this using natural logs, then we apply the natural logs on both sides. And that allows us to bring the exponent to the very front. And so I think you see where the complexity lies a little bit. So we can divide both sides by natural log of 5. So guess what happens when you divide natural log of 1 over 125 divided by natural log of 5? You will end up getting -3, and it works out the same exact way. So that's if you're curious about the natural log method, but whatever method you choose, that would conclude example 6. So for example 7, this one wants us to write this expression as a sum or difference of logarithms, and also it appends at the end to express any powers as factors. So we'll go ahead and do all of this in this problem. So again, this is a type of problem that there's a bunch of variations of these types of problems, and I do recommend you look at the notes and see other types of problems like this one that ask for the same directions and know how to do those problems. If you see some on the practice test, do those, but the best way to study for this test is to just not look at all of these examples from just the practice test or just the notes. Use all the resources. That'd be the best way to prepare for this test. But from there, anytime we want to express some sort of expression as a bunch of separated logarithms, we do need to utilize the rules. And since there is a product here, then that tells us we can use the product rule, which tells us that we can separate whatever the products are into separate natural logs with a plus sign separating them. But then it also says, to express powers as factors. So remember, the power rule is something that is a property of logarithms, and as a consequence, natural logarithms. So we can take this exponent and bring it to the very front. And the only reason we're doing this is because the problem tells us explicitly to bring powers as factors. So that is 11 natural log of x. And so technically, this part has the same condition that we need to apply. So a square root is a power. In particular, it's a 1/2 power. Remember, a square root is the same thing as a 1/2 power, and you have to be able to see that so you know to bring that 1/2 power as a factor for the corresponding logarithm. As long as you can make that determination, you would get to this right here, where everything left over in the logarithms are devoid of any powers, of any products or quotients, and that would conclude example 7 here. We move on to example 8, which is a problem from the exponential growth and decay section. This is actually one a few people had a bit of issues with, so go ahead and talk through it anyways. It says that the half-life is 1690, and we can actually use that to figure out a lot of information anyways. If you read through the whole problem, you end up seeing in general that the problem does not give you a rate, so we can figure out the rate first, as we did for other problems in that section, using the formula that I gave you here, where A is the final amount, P is the initial amount, and T is time. So since this is a half-life based problem, that means that the difference between the final and the initial amount, well, the quotient is just a half. I mean, it's half-life. So natural log of 0.5, and how much time does it take for this to become half? Well, 1690. And it seems like a lot of people were able to get to this part just fine, but half-life tells you what the quotient between the final and the initial is. It's just simply half, so that's why I put 0.5. So if anything, that's the intermediate step. We have to do that regardless of the problem. And then once we figure out the rate, now we can figure out, well, we know that the formula for exponential growth or decay follows PERT. The initial amount, they gave us 70 grams are present. E raised to the rate, which we found over here as natural log of 0.5 divided by 1690. And it asks us to find out how many in 370 years, so simply 370 for time. And once you're able to organize all of that appropriately, then you can determine what the output is. 70 e raised to the natural log 0.5, close parentheses, divided by 1690 times 370. And I get 60.1439, blah, blah, blah. It says round to the nearest thousandth. So I will go ahead and put 60.144. So that's 3 decimal places for the thousand. And that would be the answer for example 8. For example 9, this is a type of problem that we would find in the properties of logarithms section, which is one of those problems of take a bunch of logarithms and combine them to just be one. So we're not solving for anything, we're just simplifying. And again, as I mentioned in the beginning of this video, I would suggest you look back at the homework and see other types of problems that involve taking a bunch of logarithms and simplifying them down to one, or looking in the practice test and finding problems of this sort. I don't think there's too much variety in the practice test, so try to utilize the notes of the homework questions. But we'll go ahead and just look at this 2 at a time, really. So I'll go ahead and pick the first 2 sequentially. And if we were to just look at these 2, adding natural logs tells us to multiply. So that's what the product rule tells us. It's the sum of 2 logarithms. It allows us to multiply accordingly. And I'm leaving this one alone for now. We'll come back to it. But this product, once you organize everything as such, you should be able to observe that the x's cancel. And once you see that, then what we have is x plus 8 divided by x minus 8. And we'll go ahead and drop down this minus ln of x squared minus 64. Now what the subtraction tells us is, well, we apply the quotient. So what that ends up looking like, it's x plus 8 divided by x minus 8. And really what this says is this whole thing will be divided by x squared minus 64. Now this is not very practical. This is a complex fraction, which means what we have to do is flip and multiply. So these mean the same exact thing. In fact, with the quotient rule, another way of saying that is just you put this underneath 1. So this is an equivalent idea to that. And I am pretty certain that you will not get one as hardcore as this one on the test. Pretty certain. But this does end up on the practice test. And you might have noticed, you might have already done this actually. This is a difference of 2 squares. So we can go ahead and utilize that. And in fact, for good reason. Because once you apply that difference of 2 squares, so x squared minus 64 is x plus 8 and x minus 8. You'll notice that there's another place to cancel, the x plus 8's. And from here, we'll go ahead and put it up over here. What we end up having is now 1 divided by, really, x minus 8 quantity squared. You might think, all right, finally, we're done. We're not done because there's a power, but we cannot bring just that power to the front because this is not an exponential function. So instead, we have to bring the x minus 8 base to the numerator and raise that to a -2 power. And from here, now we could take this and move it to the very front. Trust me, I tried to think about a few ways of explaining this problem that were not so convoluted, and I couldn't think of anything. But this would be the final answer. So again, just be aware of these types of problems, study them from the notes or from the homework, and just be familiar and comfortable with these types of problems in review for the exam. So finally, we'll look at example 10, which goes over a few properties of natural log. So of these, domain, the range, the asymptotes, and the inverses, these are all things that you do need to know going into the test. And so for the test, you won't have to graph anything by hand like you did the previous test, so you won't have to worry about doing this. However, if they do have anything graphing, it'll either be multiple choice, or it will have this box that I kind of resembled here. So I'm gonna do one of each. So either you have to fill in the box or do a multiple choice. I'll do one of each. So the domain for this logarithmic function over here, remember the domain only cares about what's within the logarithm. Whether it's a log or a natural log, you set everything within the log. In fact, I'll do this in a different color. Everything within the log, you set that strictly greater than 0, not greater than or equal to, strictly greater than, and you solve for x. Which, well, that isn't too bad, but the problem wants you to put this in interval notation. So what is this interval in interval notation? X is greater than 4, so that starts at 4, exclusive, which means you do not include the 4, and it goes to infinity. And that would answer the domain-based problem. And so now we think about how to graph this thing. Now, for this problem, it will give you the option of graphing. In the top right, it'll have an exponential tool, a logarithmic tool. You definitely want to pick the logarithmic tool. So if you have a natural log, the base here then would have to be e. That's what ln corresponds to. It's a log base of e. And it might even default to e for you. So if it does not, then it's your responsibility to go in and change it. The horizontal stretch is always 1, we never touch that, so I'll just default that. Vertical stretch is if there's any numbers multiplying to the natural log. We don't have any, so this defaults to 1 as well. The vertical shift is how much we go up or down. We look at this problem, and we see that the +3. So the +3 here tells us that we're going up 3. And the -4 here tells us we're going to the right 4. So we can apply that as, see, vertical is up or down, and so that would correspond to 3 here for the up 3, and then to the right 4, that would be 4 right here. And if you provide all of that information, then what will happen is you will get a graph that looks exactly, let's see, we shift to the right 4, so you would get a graph that looks exactly like, actually I'll use blue. Like this. Because remember, that does formulate with the parent function that looks exactly like this. Now there was something I noticed on 1 or 2 of these, and it required you to, right after you plotted this, you also have to plot the asymptote as a dotted line. In the graph, there will be a dotted line option, and you will have to put a dotted line at the asymptote. This asymptote being at x is equal to 4. So that is something to be aware of. But once you do that, we can move on to the range. Now that we're given the information about the graph, the range, well, we go down forever and it goes up forever. So that's negative infinity to positive infinity. Vertical asymptote, well, I wrote it down right here. Another thing that emphasizes it is where the domain just abruptly seems to end at. They normally want an equation, so x equals 4 suffices. Now we move on to the inverse. Now with the inverse, so remember with the inverse you have to switch x and y and you solve for y. This is the original equation, so if you switch x and y, so we switched x and y, and then you solve for y, which means you subtract 3 on both sides. But now there's an ln in the way from y being by itself, so that's when we apply e to both sides. And an e applied to an ln, they cancel out. And finally, we can add 4 on both sides. And this would be the inverse function, e raised to the x minus 3 plus 4. And it does ask us to find the domain and range of this, but remember, for inverses, the domain and range, the domain of the inverse is the range of the original. So the range of the original is now the domain of the inverse. The range of the inverse is the domain of the original. And then from here, and we'll assume that this is the multiple choice type of problem that they will ask. They want you to graph the inverse. The inverse is an exponential, which means its shape will look like this. That is something you may want to refer to in that corresponding section on exponential functions. It says that the range starts at 4. So if you think about going down to up, it says that the range starts at 4. Exponential functions do have horizontal asymptotes, so that would make sense that there is an underlying asymptote here, and that graph in particular should be easily discernible from other graphs that may shift in various directions. But other than that, that concludes example 10 and my study guide review for test number 4.